Hey there, math hoppers. In this video, we are going to learn all about piecewise functions. So what is a piecewise function? Well, they might look strange, but a piecewise function is really just a function defined by two or more equations, and those equations are what we call the pieces. And each equation applies to a specific portion of the domain. So they can look very different. Sometimes all of the pieces are linear. In fact, sometimes all of them are constant functions, those horizontal lines, and that's a specific type we will talk about. But they can actually be made up of any type of function we have learned up until this point. Quadratic, cubic, square root, exponential, you name it, it can contain them. All right, so let's look at a piecewise function, f of x, where it is defined as the function x plus 3. So it's defined as the linear function x plus 3 when x is less than but not equal to -1. And it is defined as the equation or the function x squared when x is greater than or equal to -1. Now, important to note when you are evaluating these, if someone asks you to evaluate a point in the domain, you must first figure out which equation that point applies to. And let's look at what I mean. Let's evaluate a few different inputs for this domain. If we looked at the input f of -3, so we want to know the value of this function, f of x, at -3. Now, it's a little more work than normal because remember, f of x is made up of two different equations. We first have to figure out where -3 falls. -3 is definitely not greater than or equal to -1, so we are not going to use the x squared equation. -3 is less than -1, so here is the function or the equation that applies to this portion of the domain. Popping -3 in for x, we'd see -3 plus 3 equals 0. Therefore, f of -3 equals 0. Looking at f of -1, well, we have an equation here that says when x is greater than or equal to -1, use this equation. Since -1 is in fact equal to -1, we will use x squared. Popping -1 in, we get -1 squared. F of -1 is 1. Looking at f of 4. Well, f of 4 is a positive number, so it's definitely not less than -1. So x squared also applies to it because it fits here in the x is greater than or equal to -1 range. So 4 squared is 16. F of 4 for this function is 16. Right, well, let's graph them now because graphing is usually what causes us the grief. So we're going to graph them in parts. For all the values less than -1, we have a simple linear equation, y equals x plus 3, which we at this point should be very familiar with. So we're going to graph just the left side of this function. Now, you can do this by making a table of values, or you can kind of say, I'm going to go from -1 down a few. -1 plus 3 is 2. Now let's just leave this here. Don't put a point, don't put a closed circle or an open circle yet. Let's just graph up into this range, okay? So -2 plus 3 is 1, -3 plus 3 is 0, -4 plus 3 is -1, and we can connect our line. There we have the left side of the graph. Let's look at the right side of the graph. For all x values greater than or equal to -1, we use y equals x squared, which is the parent function for our quadratic. So again, we can make a table of values, or we can just kind of plot some points. -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. And just plot those points, draw your curve, and don't yet place an open or closed circle, because we are going to talk about why we need open and closed circles. So putting these graphs together on the same coordinate plane, we see that we have this x plus 3 line comes up to -1, and I have drawn an open circle. Why have I drawn an open circle? Because at -1, the equation x plus 3 doesn't work. It's only good for values less than -1. So at the end of this line, we put an open circle saying that at -1, this is not the line you want. You want to use the other equation. So because we have this x squared here, we have this little parabola, and that is defined for x is greater than or equal to -1, we put a closed circle here indicating this is the value you want to look for or look at for -1. All right, we're going to talk about the fact that there's a little jump here too. Normally, we see graphs of functions, and they are nice, smooth, continuous functions. We can draw them without picking up our pencil. This is not that case. This function is not continuous. You cannot graph it without picking up your pencil. We call these functions discontinuous. Many piecewise functions, not all, but many, are discontinuous. We'll work with discontinuous functions later on in this course, but this is a really good point or a time to bring it up since this is when we first see it. All right, I said not all piecewise functions are discontinuous, so let's see some that are continuous. Let's work with this one. Let's put together f of x where it is defined as x plus 3 when x is less than or equal to -1. It's defined as f of x equals 2, that horizontal constant function y equals 2 at all values between -1 and 2, but not including either -1 or 2. And it's defined as -x plus 4 for all values greater than or equal to 2. All right, let's graph these in pieces and put the open and closed circles in once we do each part. All right, so x plus 3, linear equation, super easy, not very difficult. And because it is x plus 3 for all values of x less than or equal to -1, we place a closed circle. So there we have it, just a simple linear function. Now let's do y equals 2, the horizontal function for the domain inputs in between -1 and 2. So in between -1 and 2, we draw a horizontal line at 2. Remember, neither -1 or 2 are included, so we are going to put open circles. And the last portion of this graph is -x plus 4. So that's a linear function with a negative slope for all values greater than or equal to 2, which tells me that I can go ahead and put a closed circle at the input of x equals 2. All right, now I know this is going to be continuous because the first portion ends at y equals 2, which is where the second portion is the entire time, and it's also where the third portion begins. So because of that, when I put this all together, I will get a continuous piecewise function. All right, let's talk about a piecewise function that we actually already know. An absolute value function is the most recognizable piecewise function. I know you're thinking, no, that's just the graph that looks like a V. It's not a piecewise. We know how to do that one. But it really is a piecewise function. The parent function for absolute value functions is y equals the absolute value of x. And it does. It looks like the V with the vertex down at 0. But if we were to look at each piece of this, if you're just going to look at the left side, so all values less than or equal to 0, this is really the line y equals -x, right? And all values from 0 forward, this is really the line y equals x. So the absolute function, or the absolute value function, sorry, is a piecewise function made up of 2 linear equations. And I will show you. So if we were to write y equals the absolute value of x as a function, it would look like this. F of x is defined as x when x is greater than or equal to 0, and it's defined as -x when x is less than 0. Now, it really does not matter where you put the or equal to here, because at 0, the output is the same for both of these equations. F of x equals x, f of x equals -x. If you put 0 into both of those, you will get 0 out. In fact, I have seen a third equation defined in some of these, in some textbooks. They will say f of x equals x for x is greater than 0, f of x equals 0 at x equals 0, and f of x equals -x at x is less than 0. And that would work too. All right, I know we know what this looks like. We just saw it on the last page, but let's put it together anyway. Left side of this function, y equals -x from all values -infinity up to 0. And it looks like the equation y equals x from all values from 0 to infinity. Putting it all together, we see the absolute function that we already knew. Let's look at some piecewise functions in real life. Now, tax tables are a fantastic real life example of piecewise functions. However, no one in Algebra 2 wants a tax table thrown at them, so we're going to make up something slightly easier. Rental car prices vary based on how old you are, and this is true. Between the ages of 18 and 19, you pay the absolute highest daily rate to rent a car because they're fairly convinced you're going to total their car. Between the ages of 19 and 24, you pay a slightly lower rate. And over the age of 25, they are convinced that you are responsible enough to rent a car from them and you pay the lowest rate possible. So the function for rental car rates would assign a different value, so a different daily rate for each domain interval, which each domain interval would be each age group, the three that we talked about here. So we could write this as a piecewise function for the daily rental car rate as f of n equals $110 a day between the ages of 18 and 19 inclusive, $95 a day from 19, not including 19, to 24, and $75 a day once you are over the age of 24. So look at this function here. Remember I said sometimes we have a piecewise function where you have all constant equations. So this is y equals 110, y equals 95, y equals 75, all horizontal lines. This is a specific type of piecewise function that is called a step function. And it's called a step function because the graph really does just look like steps. But it happens when each portion of the piecewise function is a constant equation. So let's look at this special step function. We have two different step functions that we're going to learn about. We have a ceiling function. In a ceiling function, all non-integers, so all non-whole numbers, are rounded up to the nearest integer. So an example of a ceiling function could be when you go to a batting cage and you pay by the hour, and you're charged for the next hour once you've passed the previous hour. And the symbolism for this looks like this. These are called ceiling brackets. So f of x equals, and the input is surrounded by ceiling brackets, where you have these little brackets with only the top bracket on them. We also have a floor function. In a floor function, all non-whole numbers are rounded down to the nearest integer. So the way we count our age is really a floor function. We say that we are 25 up until our 26th birthday. So we round our age down to the nearest year, and we don't add a year until we've passed that next birthday. And the most common type of floor function is a greatest integer function. And you may see these in your textbook. You may be asked to solve these. So we're going to look at them right now. And the symbolism for the greatest integer has floor brackets. So the exact opposite of the ceiling brackets would be these floor brackets. Now we're going to look at the greatest integer function. So for all real values of x, the greatest integer function simply says that it's going to return the largest integer less than or equal to x. Basically, it rounds down to the nearest integer. So if you put an input of 1 in, you get 1 out. You put an input of 1.5 in, you get 1 out. It doesn't round to 1, but remember, we're doing the lowest nearest whole number. 3.7 also rounds down to 3. 4.3 also rounds down to 4. Now, it doesn't get confusing until you look at your negatives. So an input of -2 would return -2. That makes sense. An input of -1.7, remember, lowest whole number, that is going to return -2. -2.1, lowest whole number, is going to return -3. And -5.5 is going to return -6. So when you are doing greatest integer function with negative inputs, be very, very careful. Now, the symbolism for these will vary. Most often, I think you see the double bracket. You could see the floor notation like we just learned in the previous slide, or some books even use single bracket notation. So I think the most often you will see this double bracket for the greatest integer function. The graph of the greatest integer function looks exactly like steps. We have closed circles on the left side, right, because you're rounding down, and open circles on the right side. Okay, let's look at an example of a ceiling function. And I kind of mentioned batting cages earlier, so let's talk about that. Let's say that the local batting cages charge $30 for the first hour and $15 for each additional hour that you are there. We could then make a table where t represents the number of hours you have spent at the cages, and f of t is a function of how much you owe. Okay, so if you spend between 0 and up to 1 hour there, you owe $30, as long as you don't go over 1 hour. Once you go over 1 hour and up until you spend 2 hours there, but not going over 2 hours, you owe $45. 30 plus the 15 for the additional hour. Once you go over 2 hours and up until you hit 3 hours, you owe 60. And I guess you can figure out what happens once you go over 3 hours. Up until you hit 4 hours, you would owe 75. Graphing this function looks like this. It is a step function. However, this time the closed circles are on the right-hand side, so opposite of what we just saw. Since the batting cages round any portion of an hour up to the next hour, each segment of the graph has that closed circle on the right-hand side and the open circle on the left-hand side. Because remember, if you spend an hour and 5 minutes at the cages, as far as they're concerned, that's 2 hours. Once you go over your hour, you have spent that next hour there. 1 hour and 10 minutes is the exact same as 1 hour and 59 minutes in their eyes. All right, remember, if you're doing your homework, if you're working through a quiz in this module, or you're doing your homework for school, and you come across a question about a piecewise function you don't understand, you should be subscribed to our YouTube channel. You go ahead and submit your questions or problems to us. We will make a custom video solution to help you out. Until next time, Math Hoppers, take it easy.